Today, I'm going to show you how to build a self-learning agent n8n that actually remembers and adapts over time, something most n8n workflows can't do. Most people think you can give AI agents memory in n8n, but the truth is they usually forget everything as soon as the session ends. What if I told you it's possible to give your AI long-term and self-updating memory so it remembers facts, updates itself, and gets smarter over time? In this video, I'll walk you through the step-by-step exact workflow that we use at the Fixen AI, where we build 5-figure automation systems for clients, and inside the Builders Lab, where we teach over 100 members how to build systems just like this. You'll see how to make an AI truly think, remember, and adapt, all in one workflow that feels alive. By the end, you will learn how to turn an ordinary automation into a self-learning system that evolves on its own. And stick around because I'll show a moment where the AI does something completely unexpected and it might just blow your mind. Let's dive in. So, before we start building anything, let's get clear on what we're actually creating. What we're building is a self-learning AI agent, basically an AI that remembers, adapts, and personalizes over time. Now, here's the problem though. If you've ever used n8n for AI workflows, you've probably noticed one big limitation. It has no built-in memory layer. Every time your workflow runs, it starts from scratch. The AI forgets everything it knew before. Compare that to ChatGPT on the other side. ChatGPT now has its own long-term memory. It can recall facts you've shared, remember preferences, and even adapt to your style across different sessions. That's what makes it feel more human and consistent. But that kind of persistent memory doesn't exist natively in n8n. So here's what we're doing. We're going to build a memory system ourselves, inspired by the Memo open source memory architecture. If you haven't heard of Memo, they just raised $24 million in Series A funding backed by top-tier investors. That tells you how serious and in demand this memory concept is in the AI space. And you can see here, it's used by many recognized logos here. If you're in the AI space, definitely Crew AI. It's an agent framework. You know, NVIDIA, they provide GPUs, AWS, and Microsoft. And if we were to look at how they approach things, they have two phases. They have a memory pipeline that extracts and consolidates. Then they have one that retrieves the most salient conversation facts, and which enables us to have scalable and long-term reasoning. You can see here, this is your message. Basically, you typing in the message and sending it in, and then we have an LLM that basically extracts this message, and once it extracts it basically extracts the facts out of the message. And then we have the update, which basically takes a look at the vector database, takes a look at the facts, and decides whether to update, add, delete, or do nothing to the vector database. Once it decides, that's basically a new memory in the vector database. So whenever the AI is going to make a reply, it's going to fetch from this vector database and extract this new memories and basically put it back here where it's going to generate a reply and you're going to get a reply back. So that is basically how it works under the hood, to give you a bit of context. And we're also going to use their prompts. Since this is an open source project, we got their prompt from GitHub. We're going to use their memory answer prompt, their facts retrieval prompts to extract the facts from the conversations, and also we have the memory extraction prompt too as well. So we are just basically taking how they apply this memory layer concept and just applying it into n8n. Here's what that gives us. That gives us an AI that can add new facts when users share something new. It can update or correct old facts when things change, and it can skip updates when nothing is new. So it just fetches the existing info from memory. And this makes our AI agent smarter because it knows who it's talking to, cheaper because we're not resending the whole full chat history every time into the prompt, which makes our prompt way shorter, and also scalable, since memory lives in the proper vector database, not inside the token context, which is basically the prompt, so which means we're using less token, which makes it cheaper. So in short, we're basically turning n8n into a foundation for persistent evolving AI, similar to ChatGPT's memory, but we're completely open source and customizable. Alright, now that we understand what we're building, let's set it up fast. So what you want to do now is click the first link in the description below and join the Builders Lab community. Once you're there, you want to make your way to the classroom section, tools and resources, and scroll all the way down till you find self-learning AI. Once you're there, you want to scroll all the way down and download this two workflows. So click on download that, and check again to download this. So once you do that, you want to make your way to n8n, create a blank canvas, and click here and import from file. And all you want to do is basically import this self-learning one, this the first one, and after that go and create another workflow. So let's save it. What we want to do, we're going to create another workflow. Let's open it in another tab and just click on import from file again, and click on the AI fact extract or sub workflow. So you save that, rename this because I already have an existing one, so it will be duplicate. So once you have this, you want to go through all of this green nodes and set up your credentials for the services that we're going to be using. You want to set up your open router, your embeddings, and then your Supabase. And after that, you also want to come here and set up your open router here, your Supabase credentials. But I believe once you have set up your Supabase credentials here, all you have to do is just select your credential that you created and just straightforward. OpenAI2 here, OpenAI2 here, and then Supabase. If you do all of that, you want to go here and basically make sure you select the workflow that you just imported, which is this one, the other one. And once you do that, you want to go here and just click on user message and just drag and drop it here. Then once you do that, you're basically ready to follow through with this tutorial. But before we get into the technical stuff, let me show you a quick demo of how this works, how it updates the vector database, or even removes or adds to the vector database. So let's get into that. So we're going to go back to the Builders Lab community and scroll all the way up and click this front end link where you can access the chat interface. And once you're here, you want to go back to n8n, make sure that you've set up both workflows. You don't need to set this as active, just set this one as active and make your way here, copy your production URL. So you've copied that, you want to go back to the front end and basically paste your webhook URL here. By the time you're probably watching this video, this will be removed and this will be a sidebar that you can hold so that it doesn't obstruct the view. So once you have set that up, you're going to create a new chat, because if, for example, if you haven't set this up, you won't be able to send anything. So you have to basically get your webhook URL from n8n and make sure it's the production URL. The workflow over here is active. Once you have set that up, what we're going to do now is we're going to test the 4 features of how this workflow works. We're going to see how it adds to the vector database, we're going to see how it updates, and we're also going to see how it deletes, and also how it works if something already exists, which means no action has to be taken. So if we give a quick look at the Supabase vector database, you can see there's absolutely nothing here, which means there is no facts inside. But over time, we're going to see how the facts are getting added, how they're getting edited, and also how they are getting removed too as well. So we're going to make our way back here. We're going to say, hey, name this applet, and I name a San Francisco. Then send that over. and we're going to wait to get a reply. And once you get a reply, we are also going to check the Supabase vector database to see if some facts have been extracted from this message that I just sent. So you can see just replied back. It said, "Nice to meet you, Ahmed. How can I help you today? If you'd like, I can help with San Francisco tips, restaurants, hikes, events, or anything else." So it's just like a normal chat GPT. And you can see here you can create new chat, and just basically like you use your normal chat GPT. And if we check our vector database here, where to refresh, we can see the first fact, name is Ahmed, which means it has been updated. Probably, let's see, second, just to make sure. So it's still executing, which means the second fact will probably be added by any time from now. So you can see it says it lives at San Francisco, and if we go back, yeah, it just finished. So I've done what we expected it to do. And if we were to go to another chat and ask, "What is my name and where do I live?" we're gonna see how that responds. So what we're gonna do now under the hood is basically just use this query and find similar queries from the vector database and add it to the prompt. And you can see here, this is another chat. You can see here it says, your name is Ahmed, you live in San Francisco. And let me even show you how it works. Let's say if the session was to end. So normally, if the session was to end, you can see everything else. One thing shows to paste it back, and we're to ask it, "What is my name and where do I live?" So in the previous session, you can see it said what my name is and where I live. But now we're going to try another session so that we can see how it's persistent. Perfect. It says your name is Ahmed and you live in San Francisco. So what we're going to do now is that we're going to test the update feature. We're going to say, "No, I live in Nottingham." And all we expect this to do now is that basically going to update this lives in San Francisco to lives in Nottingham. So we're going to see that. So that basically said times of the correction, you Ahmed and you live in Nottingham. And if you were to check the vector database, normally it takes some time for it to update. It's probably still running to check the facts here. So it's still running, so you'd have to give it some time. Perfect. And I just updated it. Before it was lives in San Francisco, now it says lives in Nottingham. Now let's add another thing. Let's test the delete feature. Let's say I don't live in. So what we expect this to do now is we're expecting it to basically delete this entry. Thanks for the correction. I'll update that I don't live in Nottingham. I have your name as Ahmed, what city, and so it basically acts to update the facts where we database. We could update this further or make it even better by basically making it more chat-based without asking these questions. So it basically does the updating in the background, so it doesn't have to ask for this and that. And if we were to check, let's quickly refresh, boom, it just deleted that complete entry, which means everything is perfect, which means it worked as expected. So now we're going to see how it works if there's nothing to extract from the memory. Let's say, what is 1 + 1? This is just a random. There's no facts on this message. So we're going to basically expect the vector database to still have this number of facts inside it. It should give us 1 + 1 is 2, but what we are going to check is basically to verify that nothing has been added to the vector database, because there is no facts to add from 1 + 1. Maybe you might say Ahmed likes maths, but that is not a fact. So let's see. Probably still 1. And you might also see, why are we getting a chat response before it updates the vector database? We do that so that we save ourselves some time, because imagine you send a message and it takes this long for the chat to get back. So we enable this feature here which says we shouldn't wait for the sub workflow completion, because we don't require anything from the sub workflow in order to process this AI response agent, because it already has the context of that pass message in the user query, so you can use that. And for the pass queries, it probably would have added those to the vector database by the time the user has typed in the next query. And if we were to check right now here, you can see nothing has been added, which means it has basically passed the test and for all the 4 core features of how this AI self-learning agent works. Now, if you are a technical person and you would love to know the insides and outs of this system, let's jump into that, and also ways that you can customize it to suit your needs. So let's go ahead. So we have 2 workflows. We have the main self-learning workflow, and then we have a sub workflow, just so that this main workflow wouldn't unorganized and just make people confused, because the AI facts extractor sub workflow is quite huge. So we just try and differentiate them, and then we just execute it as a sub workflow. And also another reason why you make it as a sub workflow is that, as you can see from the demo, the execution of this takes a lot of time. So we just make it just run the sub workflow on its own, and then we go ahead with the next node, which is the AI response node, which generates the response. And if you were to go into this one of the past executions that we did, we can see we received a webhook from the front end. So we basically use Lovable to create the front end, and then it basically takes our input and sends it back to our n8n backend. And how the n8n backend receives it is through this webhook node. You can see it put in the headers, and it also put in the body and the session ID. Think of the session ID as this basically. So each chat has its own session. So probably if we send a message from this chat, it would have a separate session. So going back, you can see our user message was what's 1 + 1, which is our last message from this session. And what it does next is that it executes this sub workflow. And if we were to check what it did, let's go to one of the executions. This will just be showcasing how it does for the none. So we have to go in here, we'll see it executed from another workflow, which is the self-learning workflow. And we have a facts extractor agent that basically extracts the facts from a current chat. As you can see here, the output was that there were no facts, because there's no facts that you can extract from what is 1 + 1. And the prompt that we provide it with is basically the prompt that we get from the Memo open source project, where you got their prompts from their GitHub. And we provided this prompt. If you want to have a deeper look of how their prompt looks, you can download this workflow and check how it works. But let me just give you a quick overview. So we can see here we're using this fact retrieval prompt, which basically says you are a personal information organizer specialized in accurately storing your facts, user memories and preferences. Your primary role is just to extract relevant pieces of information from the conversations and organize them into distinct manageable facts. And this allows us to easily retrieve and personalize for future conversations. Below are the types of information you need to focus on. So it gives us this basically role or persona prompt, and the types of information like store personal preferences like likes, dislikes, specific preferences, and maintain important personal details, track plans, remember activity, monitor health, store professional details, and miscellaneous information too as well. And it gives us a format of the input and output, basically using a few short prompting technique, which you can see here. It gives us multiple examples of input and output examples, which basically makes the output of the AI consistent. It also gives us things to remember to as well. It gives us the date, like what to not return and stuff like that. So this is a quick overview of how the fact retrieval works. And then you can see here it gave us no facts, but I believe this would be a better example to show if we added something. So let's go into one of the executions that we added something. So if we were to check, we can see here, it basically extracted this thing that I said, no, I live in Nottingham, and I extracted the fact that said, okay, lives in Nottingham. After that, we use a split out node, because sometimes there might be more than one fact, there might be two facts. You could possibly see that if you go to this execution here. Okay. By going into this execution, you can see we have two facts. We have name is Ahmed, lives in San Francisco. So we split it out into two different items instead of one array with two items. So we split it out, name is Ahmed and lives in San Francisco, so that we can work on them individually, so that each fact is updated after the other and not doing it together, because some facts might contradict with the other fact. So we just make sure that each fact is done after each other. So we use this loop over items because, as I've told you, we don't want to have facts complete. A fact complete in the sense that, let's say this fact might contradict with the next one. So if you update them together, we might not have an accurate vector database of facts. So we just make sure it's done after the whole process is done, then we do for the next fact. So we use this loop for that, and then you can see here, we go to the first execution, we are using the first fact, which is name, it's Ahmed, and then we use this fact update agent, which basically takes the prompt from here. We have to scroll all the way down, second, and we use this default memory update prompt, which says you are a smart memory manager which controls the memory of a system. You can perform 4 operations. You can add into the memory, you can update into the memory, you can delete from memory, and no change, which is basically what I showcased during the demo. And based on the 4 operations, the memory will change. So by adding, you're basically adding to the memory, update, seeing delete, you're deleting, none, you make no change. And if we were to open that, you can see the prompt is basically here, and it gives us specific few shot, or should I say this is a one-shot prompt example for each operation. For add, it gave us this. So this is the old memory, so it basically retrieves from the vector database using how normally a retrieval augmented generation will work, but this one we're just retrieving from the vector database. So it finds facts that are similar to the existing facts that it extracted from this fact extractor. So once we retrieve similar facts, so like let's say for example, let's say lives in Nottingham might be here, but then what we have here is lives in San Francisco. So it's going to find similar facts on the vector database that relates to this. Once it does that, if we were to go to update, you can see it basically updates it and says this is the old memory and this is what you should update it with. So it's basically going to say, okay, from live in Nottingham, update it to lives in San Francisco. So that is how the update works. And the add is just basically, if let's say that from the user query, if you were to extract a fact and you were to pass it on to this agent here, which is the fact update agent, and the fact update agent was not able to retrieve anything similar to that query from the vector database, what that means is that, okay, we need to add that new fact because it doesn't exist, so it's a new fact. So we have this output example which just says, okay, add name is John, and it gives us an ID. And this is also, like, let's say, a similar, but then it's not similar in the sense of name, it's similar in the sense of user as a software engineer. Because you know how vector embeddings work, they find the words that's similar to the query that you provided with. So this is the most similar that I found, and then so that it doesn't relate. It relates in the sense of, okay, this is their job, this is their name, but it doesn't relate to the fact that, okay, it's both name, because someone's name cannot be a software engineer. So, which means it's adding to that vector database. So that's how the add works. And the delete is basically, it checks if what exists in the vector database contradicts what the user query said. So if the user query basically said, I don't live in Nottingham, and in the vector database there's a row that says, okay, or a fact that says lives in Nottingham, which says lives in Nottingham, and as you can tell, those two facts contradict each other. So we need to delete the existing fact from the vector database which says lives in Nottingham, and basically no need to add a new database or update because there is no new facts to update it with. So it says here delete. So you can see the example here from the existing vector database. It says loves cheese pizza, but here from the user query, which I see in a fact like extracted from the user query, it says dislikes cheese pizza, and you can see this contradicts this, so we delete this fact from the vector database. And for no changes, let's say if a fact already exists in the database and the query that the user, or should I say the facts that were extracted from the user query, is basically the same fact. You can see here there's an existing fact in the database that says name is John, and the retrieved facts from the user query says name is John too as well, which means the same, so there's no need to perform an action. So that is what this AI fact update works. As you can see here, we provided it with lives in San Francisco, and if we were to check what it retrieved, we can see it retrieved, if we were to check it here, it says name is Ahmed, which is basically what it retrieved from the database. The name is Ahmed and lives in San Francisco don't relate with each other. It just says, okay, name is Ahmed, which is the name, lives in San Francisco is where Ahmed lives, so it doesn't relate. So that's another fact we can add, which made it an add event. So then the output, once we take the output, we can see this is a stringified JSON, and then we parse it and turn it into a JSON object, which gives us an ID, lives in San Francisco, and the event type, which is an add event. So we use this to basically check the length of the parse JSON, because sometimes the AI might output more than one operation to do. Because if we check the prompt here, you can see sometimes it gives us a none and delete, or like an update, non-update. So we'd have to do 2 or 3 of those operations separately, so that, as I've said, nothing contradicts or conflicts in the database, so that we make sure everything is up to date. So we use this to basically check the length. If the length is more than 1, we basically split it out like we've done before, but here we're not splitting it out because it's just 1. The length is just 1 because it just gives us 1 operation. But if we were to have memory 1, memory 2, memory 3, it would basically split out using the split out node. Then we have the switch node, which basically decides on which operation to take. You can see there's add operation, delete, update, and none. And the way it determines that is by basically checking the event operation type. Could be add, could be delete, could be update, and it could be none. So depending on which one it is, to the right path. You can see here it took us to the add path, which is correct. So we're going to add lives in San Francisco to this vector database. And the way the add fact works is that we first take that fact, which is lives in San Francisco, and then we turn it into embedding. Embeddings are basically the representation of a sentence in numbers in the vector space, basically. I want to go too in depth into that, but we basically take that and then we turn it into embeddings using the OpenAI embedding 3 small model, and then we pass in the user query here, which says lives in San Francisco. And then this node, what it does is that it basically takes the user query, first turns it into embeddings using this embedding model. You can see multiple numbers. Then it adds it to the database, which is the vector database. So it would add another row here which says lives in San Francisco. So that is how the add works. How the delete works would basically be, let's go to an execution that should explains delete. So here we have an execution that basically represents how delete works, and it also has more than one operation, so I can explain how this split out node works. So you can see here from the output we have more than one operation. We have none and delete. Delete in the sense that okay, lives in Nottingham contradicts does not live in Nottingham, so we're going to have to delete that. And text is name is Ahmed, and probably if we check from the extracted, we can see name is Ahmed. So there's no need to update this fact because it already exists in a vector database. So we get two operations that we need to do. We have to first delete and do nothing with name is Ahmed. And then we use this if else statement to basically check the len. In this case, it's more than one, which we have two items there. And then basically split it out using this node, which turns this into this basically so that we can execute each operation independently. So that's basically how the split out node works. So what we do for the delete is that we first get the ID of the fact that we want to delete. The fact that we want to delete lives in Nottingham because it provides us with the fact from the fact update agent, which is this one here. So we first get the fact from the database. It could be an ID 8, 9, or 10 depending on how depending on when the fact was added. So you can see here we got the fact, and in this case it was an ID 10. We have the embeddings of this text here, which is a numerical representation of a text in a vector database, which I say in a vector space. And then what we do next is that once we fetch that fact, we basically use the Supabase node to delete that fact, which means it doesn't exist from the database anymore. So that is how the delete works. And how the none works, it basically just reroutes back all the way here and nothing. So now the final one is update. It implements techniques from both the delete and the add, because there is no node in n8n, or should I say for a vector database, that you can use to basically replace the fact, basically replacing the fact by meaning, okay, we keep the same ID, or all we have to change is change the content and change the embedding. So the way we have to update, or should I say the workaround, is that we have to find the fact that we have to update, delete it, and add a new fact basically. And if I was to go and find Fusion, I had the update, which is this one here. We can see first we get the ID of the fact, which is lives in San Francisco, which is the old memory. In this case we use the old memory here. Then we get the ID, which is a 9, and then we delete it from the vector database. So which means that fact does not exist now. So we have to add the new updated fact. So when adding the new updated fact, so you can see this is the old memory, which is a fact that we just deleted. Now we're going to add this new fact, and it says it lives in Nottingham. So basically going to apply the same technique we used here. We're basically going to turn this, if you go to split out, we're basically going to turn this lives in Nottingham into its numeral representation, which can be put in a vector database and can be used for vector search and stuff like that. And then we pass it along the new updated memory, which says lives in Nottingham. This one is the old memory, so ignore that. But what we're providing here is the new memory, which is lives in Nottingham. And what this basically does is that it first turns it into an embedding form, then we add it into the Supabase vector database, which you can see here, which probably from our demo we would have deleted it, but it would have shown here. So that's basically how the fact extract or sub-workflow works. And once it executes that, you can see it takes quite some time. So that is why we just don't wait for the sub-workflow completion to come. So that is why we don't wait for the sub-workflow to complete, because you can see it takes time, and it would make the response from the front end take quite some time and be quite bad for the user experience. So we just let it run on its own, and we just proceed with the next node, which is this AI response agent. This AI response agent uses the prompt from here if I scroll all the way up, which is the memory answer prompt, which says you're an expert at answering questions based on provided memories. Your task is to basically provide accurate and concise answers to the questions by leveraging the information given in the memory. So what it does here, as you can see, we have 1, 2, 3 tools that we give it. First is the chat model, obviously, the brain, the simple memory, so that it can have context. This is not a persistent memory like this one. This basically just exists in the session one. So wait, let me show you a sec. So the memory would basically exist for this, for just this chat only. If I was to open another chat, here, it wouldn't have context of what was said in this conversation. It would just have the facts, which is the persistent memory, basically, if you get what I mean. So if we were to go back, basically it's a simple memory that saves the last 10 conversations, which you can see here, chat history. And then for open router, we use the GPT-5 model. And then this is basically the RAG in the sense that we are fetching facts that are similar, or should I say that would be needed to answer the user query. For example, if a user query is, what is my name? We would use this RAG tool, which is the AI fact extractor, to basically extract similar embeddings that relate to the word, or should I say that can help us answer the query in a sense, okay, where do I live? And it checks, and then the vector database that checks, okay, is there a fact that says, where does this person live? It might say, okay, the vector database might say, okay, lives in Nottingham. So we're going to fetch that ID, and then we're going to add it as context to the AI response agent. We were to check what was said here. It basically said, what is 1 + 1? But I believe this wouldn't be a good example to show you. Okay, so you can see this one asks, what is my name and where do I live? And what this fact extractor, you can see here, it says, analyze the user query and extract all facts and information relevant to the question. Focus only on details that can help answer the question query accurately, and you choose the top 5 most similar facts that can help us answer the question. And what you can see here, it basically extracted the first one, says lives in Nottingham, because it helps us answer the second part of the question, and name is Ahmed helps us answer the first part of the question. So, and then the way a RAG basically works in completely high level terms is, it basically takes the user query, which is this, turns it into an embedding, which is the numerical form of this text, and basically, as I've told you, finds, based on this description, finds information relevant to the question that can help us answer it. So in this case, turn this, and using the vector embeddings of the existing facts, it compares and sees which ones are the closest to each other in the vector space. So once it retrieves that, it passes it to this AI agent as context, along with the prompt that I showed you from here, and basically answers that question. And here is the system message where we put the prompt, and think of the user message as basically what you type in to normally ChatGPT, or should I say what you would normally type in here. So we provided with that, and using the context that I received from this vector database, it basically said your name is Ahmed and you live in San Francisco. And then once we get that answer, we respond back to the webhook. If you can remember, we send each chat conversation to the n8n backend, which then receives it using this webhook node, and then it responds back to the API call that was made, and responds back with the response, which says 2. So that's basically how it works. I know it's a lot, but it's actually a genius way to implement this feature. In case you might want to change the model that you want to use for answering the questions, you can change using this open router chat model. Let's go back to editor here. And the benefit of using Open Router is that it gives us the ability to choose any model we would like. The Open Router is a software which gives us a unified interface to access different models. So you don't have to create an account, let's say, for Google if you need to use Gemini 2.5 Flash, or OpenAI if you need to use ChatGPT, or for Anthropic if you need to use Cloud Sonnet. It gives us one unified API to access all of these models, and not just these models, but a lot more. And you can see here, it gives us a lot of different open source model too as well. So now, for the curious ones, let's go ahead and basically show you the cost of running this whole system. It's probably not much, but just to give you a bit of context of how much it costs you to run this. So you can see here, we'll be basically breaking it down by the technology you use, which is Open Router, the embeddings, and the Supabase vector database. It doesn't cost anything. The embeddings cost almost nothing. And then for what mainly costs money is basically the GPT-5 model we use for responding to the chat. You can see here, for 1000 chats, that is, for context, I better go to the front end. So 1000 chats, this for context is just 4 chats, and 1000 chats with more than 20 conversations, back and forth conversations. So you can imagine how many conversations you can have. Let me even context 20 times 1000, that's like 20,000 conversations for just $6.25. And for 10,000 chats, 10,000 times 20, probably gonna give you 200,000. Maths, it's bad. Anyways, so wait one sec. Go back to the cost breakdown. Slaves. Yeah. So it's going to cost us $62.50 for over 200,000 conversations. No, you probably haven't had I know I probably haven't had 200,000 conversations with ChatGPT, and I know I almost use it every day. And this one is like, I believe, based on my maths, let's try my math. I believe this would give me about 2 million conversations. Let's see if I'm right. So let's do it. Yeah. Yes, I'm right. Still have my maths in check. So you see this. So for all 2 million conversations, it's gonna cost you $625.40. So that's basically the cost breakdown. Let's quickly wrap up what we covered today. You've seen how to build a self-learning AI agent in n8n that actually remembers, adapts, and improves over time, solving the problem of AI workflows that forget everything the moment a session ends. If you want to take this further, join the Builders Lab, which is the first link in the description below, and get access to a practical step-by-step version of this video you're watching, plus templates, live sessions, one-on-one sessions with me where you can ask me any question, direct support so that you can implement the system faster and more effectively. And if you need a custom automation built for your business, check out my agency, which is the Fiction AI, which is the second link in the description below. Don't forget to like, comment, and subscribe, and I'll see you inside the Builders Lab community. I'm Ahmed, and see you in the next one.